This is a talk about real-time open source video processing and communications. The problem is, if you want to build an application, there are so many options, it's hard to know what to choose. So I was facing that problem. I did some research, I did a talk on it, I did a 10-page paper that's now published on the German National Library website. But there was still no more content, so I created a wiki, wiki.pythonlinks.info. Here's the QR code to go to it. If you want to learn more about any of these topics, they're all mentioned, they're all discussed in more detail in the wiki. This talk is just a general overview. And the feedback was really good. Two different people said it's a gold mine of information. That's really what it is. A lot of work went into putting all of that content, aggregating all of that video-related content on the site. So today we'll be talking about applications. The idea is to give you sort of the context of what we're talking about. We'll talk about the cameras, the image processes, the FPGAs, communication, and what recommendations, what technologies should you use for your applications. And this talk does not cover desktops or cell phone applications. It's more for real-time control stuff. It's also not a class on FPGA development. In 45 minutes, I can't teach you much about FPGAs. It's a completely different mindset from being a software developer. What I recommend is, if you're interested in learning more, sign up for Silesian Polytechnical, has Mikroinformatyka Systemów Cyfrowych, Studia Magisterskie, it's in Polish. I was in the first batch of students from there. They did a brilliant job. The curriculum was set by Intel. Intel paid the professors some extra money. The documentation was great. The classes were relevant. They didn't waste barely any time on useless material. Actually, the head, Professor Czerwinski, was really amazed when I told him the training was better than at MIT. So anyhow, he was flattered. The problem is that they're targeting major corporations where each developer builds a small segment of a larger system, typically ASIC or on verification. And it's very different from the startup community where you're pulling in chips from multiple sources and you really care a lot more about the communications protocols. So it took a long time to learn about all of these communication protocols. Here's an overview. So here's what you can do on an FPGA, which you can't do on a microcontroller. FPGAs are basically circuits that are very good for doing video processing. What you have to do on this is read and write from multiple memory banks at the same time. And here's another application. You can imagine doing this in Ukraine where you're not tracking cars, but you're tracking tanks. And so the problem with this is done with AI, and so every hour of video takes 6 hours to process. Not good for a real-time battlefield situation. I suspect you could do this much faster with FPGAs. Let's talk about another drone application. People want to do drone controllers. It's basically an asymmetric application. You have a very low bandwidth going up to the drone. Absolutely critical that those commands get through correctly. Much higher bandwidth video from the drone coming back to the ground. It's okay if you lose a few pixels. So one direction of this pipeline, it goes from the camera on the drone and through a MIPI CSI interface, goes into compression, gets encrypted, gets IQ encoded so it can drive the radio. The radio waves get transmitted, received, IQ gets decoded, gets decrypted, decompressed, and displayed. And then the commands go in the other direction. Sorry, I'm not allowed to say more about how all of this stuff works. But the problem is in Poland, as soon as you're doing military applications, you're subject to a whole stack of government regulations. And it's not only government regulations, but it's also cost. So even before you ship a product, you're subject to these regulations. It's very off-putting. So I decided let's focus on agriculture. Agriculture is going to be a huge problem. First of all, we have climate change. Food prices are going up steadily. Large amounts of hunger, particularly in Africa. The refugees are coming north. And then on top of that, we now have the fertilizer from the Gulf of Hormuz is blocked, so some large amounts of fertilizer. So food prices are going to continue to go up. Agriculture is a great place to be. What can you do with FPGAs in agriculture? Well, here we have the photosynthesis spectrum from growing plants. So the sun shines down, they absorb some water, and they generate this spectrum. And you can actually measure this spectrum. In fact, the government does measure the spectrum. The government overflies the fields, uses this to measure the health of the plants, and then the amount that the farmers get paid is dependent upon those overflights. I spoke to one group here. They use the DJI multispectral camera. It's got 4 spectral cameras on the top row, red, green, blue, and infrared. And on the bottom row, it's got the navigational camera. The problem is, if you look at the specs, here are the frequencies they measure, and they don't line up. It's great for a general purpose camera, but it doesn't line up with the photosynthesis peaks and valleys. So you're not getting an as accurate a reading of the health of the plants as you might. What you'd like to do is create an open source camera that actually measures the peaks and valleys, and then release that as open source so that farmers all over the world could use it and could use that to increase their production. That would bring down food prices. There would be less hunger. Good thing all the way around. The other problem we have is with water. So the camera we just spoke about and the frequencies we just spoke about are either in the visible or in the infrared, but in the near infrared. Also later we'll be talking about radio waves on the right hand side. But the key water peaks are in the shortwave infrared. So here you can see the water absorption spectrum. You really want to measure at the peaks of the water absorption spectrum, but both of those peaks are outside of the infrared and they're outside of the near infrared. And so you can't watch them with the inexpensive cameras. You need these very expensive gallium arsenide cameras. Sort of not a mass consumer product. Okay, let's look at another interesting application of FPGAs in real-time video processing. Here we have the frame glasses. It's got an embedded camera, it's got some batteries, it's got an FPGA, it's got a microcontroller that speaks Bluetooth to your cell phone. Basically, you can take a picture, it goes through the camera pipeline, it goes to the microcontroller, it gets submitted to your cell phone and off to the cloud, and the answer comes back to the microcontroller, to the FPGA, and it goes through the display pipeline and gets displayed. Here we can see the details of the camera pipeline. There's a camera. You get some MIPI signals with a MIPI DFI to absorb it. It gets turned into bytes with pixels. It gets debayered. We'll speak about that in a moment. It gets cropped. We'll speak about that in a moment. It gets JPEG encoded. We'll speak about that in a moment. And eventually it goes into the large RAM and sent off to the microcontroller. And from the microcontroller off to AI and back through the rest of the pipeline. So let's talk about the different pieces of these video pipelines. On the left we have what used to be called a camera. Nowadays when people speak about cameras, they think more about a cell phone. They can have multiple lenses, range sensors, integrate the information from the different cameras in real time and generate videos. Just amazing what these cameras can do. But typically what the engineers are concerned with is something more like the Raspberry Pi camera. So for about 50 euros, you can get 12 megapixels at 60 megabits, 60 frames per second, and you can plug it into all kinds of things. If you only want 5 megapixels, here you have the fisheye lens, the Waveshare OV5640. Fisheye lens does not need to be focused, only at manufacture time. And after that, but if you want a rectilinear lens, it's a bit more expensive because it needs autofocus. It also has a flash, comes in at 26 heroes. If you do a zoom in, you can see the pins. That's not a, I think it's 18 pins, not enough for a 24-bit RGB signal. But you do have that white is either called flexible flat connector, or some people call it a flexible printed connector, FPC or FFC. And then they'll take a MIPI signal out to your favorite device. There are a number of ways that these cameras and things are assembled. So here we have the ArduCam USB shields. The bottom board is either USB 2 or USB 3. The top board is one of very many cameras, and the middle board is a smaller number of bridge boards, adapter boards between the cameras and the USB bases. There's also this gorgeous camera, completely open source. It has a place for a camera, place for a microcontroller, place for a communications board. The microcontrollers often get very hot, so the whole case is metal. So the whole thing looks really nice, and they've got a base that you can drive and rotate in 2 axes. Very nicely done, all open source. The only thing is there are no, when I last checked, there were no FPGAs supported. We have lenses. In college you may have studied traditional lenses, something like this. But of course, like everything else in the pipeline, it just gets more complex. So here we have the 2016 iPhone lens patent. The interesting thing is the design tools are much better now, and so one can actually design and calculate how these lenses operate. Then we get to the image sensors. There's a website that lists 874 image sensors. Actually, I checked it, and you can, very nice search options. I checked it about 6 months ago, and it also had 874 image sensors. So that tells me that it's just not being updated, which is kind of sad. And of course, it doesn't even list all of the image sensors. Some of the not listed ones are at the bottom of the page. What goes on these image sensors? Well, they're not just image sensors, they have complete image processing pipelines. And often you'll actually get ASICs which have image processing pipelines without the image sensor. So a whole bunch of things can happen on these devices. The first one is often defective pixel correction. So if you have a short circuit on a black background, you're going to get a white dot. And if you have an open circuit on a white background, you're going to get a black dot. And so you really want to correct both of those. Historically, there were a lot of bare filters. So the idea is you have on the upper right-hand corner, you have the gray sensor background, and then you put various inks, filters of different colors, and then you get a measurement of what the brightness is of each color at each of those grid points. Wikipedia has a very nice write-up about this. So image number 2 is what the gray board measures. Image number 3 is that same signal, but with the either red, green, or blue pixels displayed, kind of the raw output. Image number 4 is what happens when you interpolate all of that, and image number 5 is if you use a proper RGB camera, for example, for example, a film camera, what you would get. And so the bare filter actually increases the bandwidth required, because for every point on the grid you end up from one color to 3 colors, so you're tripling the size of the output image. But these cameras have so much size, right? My desktop monitor has what, 1.5 megapixels or so, and you can easily get 5 or 12 megapixel cameras. So it makes much more sense is to do pixel binning, and then you get some averaging, reduce the noise. And so you can bin horizontally or vertically, but typically you bin by a factor of 2 in each direction, so you get a quarter as many pixels out. Great. That reduces your bandwidth, so that's good too. Another process has to do with correcting for the spectral response. So the camera RGB has a certain spectral response, the display has a spectral response, the eye has a spectral response, and they're all different. So if you do it without correction, you take a photograph of this woman, on the left-hand side she looks like a zombie or something, the color of her face. on the right-hand side, it's been corrected and she looks perfectly normal. So for evolutionary reasons, people are very sensitive to facial skin color. You want to stay away from the sick. But we don't care as much about the background green. So color balance and rotating the colors is really important. Another rotation of colors is the RGB to YUV matrix. YUV started with the black and white TVs, basically grayscale, and they wanted to both support the old signal and do color TVs. So what they did is they just added the other two, the U and the V color planes. You can see on the left is the original image, on the second to the left is the grayscale, and you've got the two color images. You can put them all together. And so the human eye is much more sensitive to grayscale than it is to the colors. So what they can do is they can reduce the bandwidth of the two images on the right. There's some complex techniques for how they do that. And then your whole bandwidth gets reduced. So that's used for devices like this one. This is a DVI to USB 3 dongle. Often we have a DVI output, but we'd like to display it on a computer or display it to others on via our computer. And so it's great. These dongles are less than $10. Make sure you get the 5 gigabits. Make sure you get the USB 3 version, not the USB 2 version. And the way that this works, it has another interesting process, which is a double frame buffer. So the HDMI signal comes in. Somewhere along the way, it gets converted to YUV. And then it gets written to one of these double frame buffers, and in the meantime the other frame buffer is sending out to USB 3. And then whenever the frame changes, the two interchange, and now USB 3 is sending out the new frame buffer and the old frame buffer is being written to. So frame buffers are a very important part of image video processing. And the problem is the microcontrollers don't have, actually FPGAs also don't have very large frame buffers. We'll come back to that in a moment. So here we have video cropping or digital zoom on a desktop. It's really easy to do digital cropping or digital zoom. The picture you save is different. But on a real-time control situation, you want to make sure that the whole display is filled. And so if you crop it, you also have to stretch it and align it. So actually a friend of mine is doing this, and so he is using the Pipeline C software for it. So the pixel stream comes in, it gets cropped, it gets scaled to the right size, it gets positioned in the frame buffer, and then it goes out to the display. So Pipeline C, if you're a C developer, then obviously something like Pipeline C makes sense to you. JPEG compression is another important process. Basically what you do is you assume that the image is the sum of several of these. So each of the colors in the image is the sum of several of these blocks times some scale factor. So it's reasonably easy to decode this. You get a couple blocks, you know which the blocks are, you know how bright they are, and you add them together. Encoding is more difficult because you have to calculate what the coefficients are for all of these blocks and then choose just the largest few. So this is pretty good and pretty fast, right? Because it's 8 by 8 pixels. So if you're doing this on a drone, you only have to wait 8 lines of display before you can send off the compression. So that's good. H.264, H.265 pattern compressions, they can compress, maybe compress things twice as far, require half as much space as the previous ones. And they also, part of how they do that is they allow for the image to shift in multiple directions by a small amount. So it compensates for motion. And H.265 also does, it can use variable size blocks. And it also can do continuously changing values. So all kinds of techniques, all still patented. For edge detection, a lot of people are interested in edge detection. For edge detection, it's good to, a lot of people use Sobel and grayscale, so it's basically pretty simple multiply to convert to grayscale. And of course the green is weighted more heavily. Yeah, there's some tricks you can do on FPGAs to use slightly different coefficients and shrink the size of your multipliers. Sobel edge detection, very simple. I'm convinced you can do better than this on FPGAs. Canny edge detector, it kind of does some Gaussian averaging. The problem here is the divide by 159. Even if you turn it into a multiply, you end up with a lot of multiplies. It can be done. Here we have the output of a canny edge detector. It looks really impressive, but actually it only shows you where the edges are. It doesn't actually tell you which groups are which pixels are in which group. This is the area I'm working in now. Okay, so those are some of the very many video processes that we can use. Where do we run them on? Well, if your bandwidth is low enough, you can do them on a microcontroller. My recommendation is use libmpix on Zephyr OS. Libmpix supports auto exposure, black level correction, white balance, debayer, color calibration, gamma correction, Gaussian blur, median denoise, sharpen, Sobel edge detection, resizing, image statistics, sampling, and JPEG compression. I read all of those not to bore you, but just to show you how many different processes there are. And this is just a small subset of what's available out there. So the way that libmpix works, remember they don't have much memory, and so they have a ring buffer. The pixel comes in and gets written to somewhere in memory, and while it's waiting for the next pixel, it can process them, and then it gets sent out from the end of the ring buffer. So very, very interesting. And very shortly they'll have single instruction multiple data, so it'll be able to do even more faster. Maybe they have SMD by now. But really for video processing applications, you really want to use an FPGA. The big names are, of course, Altera and Xilinx. When I was recently using Altera, a year and a half ago, it kept crashing on me. No, thank you. It takes Xilinx. The big firms have a conflict of interest because they both sell the FPGAs and they want your circuitry to require the largest FPGA, but they also sell the tools, and you want the tools to create the smallest possible circuit. So there's a conflict of interest there. There are also a bunch of Chinese companies, 10 Chinese companies, most we never even heard of. One group that is doing really well is eFinix, and I believe that they're the same company as Pango. So I don't know for sure, but when I looked at the Pango specs, they all are the same, have the chips sold by Pango are all the same specs. And when I spoke to my Taiwanese friends, they said, oh yeah, the Chinese companies often hide that they're Chinese companies. These guys have completely different websites. So if you're not sure if a product is Chinese or not, just check with your favorite Taiwanese friends. And of course, Taiwan's doing a massive investment here in Poland to help export Taiwanese products. What I really like is the Yosis open source synthesis suite. It's really runs on my Mac. It's really fast, usually just a couple seconds to synthesize, place, and route. It's evolving incredibly fast. It's got so many eyeballs looking at it, fixing all the bugs. Really lots of fun. Very enjoyable work. The cheapest product, sort of with significant bandwidth, is the Tang Nano 20K. It's got both DVI, it's got that FPC connector, it's got a bunch of memory on board. The problem is it's not quite clear what the licensing is on its code. And the bigger problem is that, let's face it, China's a dictatorship. It's tremendously helped the economic status of all the Chinese, but the Chinese employees are kind of abused. They say we have to work 9 to 9 by 6, which means 9 in the morning till 9 at night, 6 days a week. We also worry about their environmental regulations. So anyhow, maybe it's better to get a Taiwanese product. One of the chips which I believe made are Taiwan is the lattice chips. ICE40 I used in a previous project. The problem is it's underpowered compared to the RP2350. So ICE40 is about $8 chip. RP2350 is a couple dollar chip. The ICE40 is limited to 50 or 70 megahertz, depending upon which circuits you're using. RP2350 has will run at 150 megahertz. ICE40 is limited to 8 16-bit multiplies. RP2350 has 2 floating point multiplies. So hard to compete there. ECP5 is much more interesting. It's got a great ecosystem. It supports 1920p, DVI, HDMI, all kinds of great things in the ECP5. Although reportedly there's now like a 1-year backlog if you want to order one. So it's kind of shocking to me. Lattice also makes the Crosslinks NX 17, 33, and 40. They have MIPI hardcores. 17 and 40 are open source, 33 is closed source. The 17, 33, 40 MIPI cores will do 2.5 gigabits, either CSI2 connect your camera, or DSI, or do 2 cameras, whatever your choice is. The 33 is interesting, and particularly the TinyVision CL-UNX33, which includes USB ports, USB 3 ports. So all kinds of good stuff out there. The one I find most interesting is the 79 iSPI 0. It includes a DVI port, and it also is Raspberry Pi compatible. So you can connect a Raspberry Pi 0, $10 for a single core, or Raspberry Pi 2W, $15. It has the FPC connector, it supports MIPI CSI, and then it's got the, you can use a parallel DVI to communicate the video signal off to across the Raspberry Pi ports over to the iSPI 0. There's also the European Cologne GateMate, which has a great strength and a great weakness. The great weakness is it doesn't natively support high-resolution DVI, but it does have this 5 gigabits per second SerDes connection, which we'll get to return to in a minute. First, but to understand that, you need to understand signals. So basically, the basic signals on a circuit board are single-ended. 0 to 5, 0 to 3.5. The voltage keeps dropping with the newer circuits, at 2.8 I think now. If it's camera to processor, you get a whole bunch of wires, like 28 or so. Digital video port. If it's called camera to display, it's called digital parallel port, digital parallel interface, DPI, or RGB. But that's limited to somewhere around 100 megahertz, maybe 80 to 120 megahertz. It depends upon if it's on the same board or how long the wires are and other things like that. And if you want to connect a FFC cable into it, you've got these boards like this RGB LCD hat, which will do the connection. Okay, but really for video, the bandwidth is pretty high, so you really want to use differential signaling. Let me correct that to say, you can do some low-end projects using DVP, and people do, but for higher bandwidth, you really want to use differential signals. So differential signaling is used by a whole bunch of stuff: DVI, HDMI, USB, MIPI, DisplayPort, PCIe, DDR/SD RAM, Ethernet, LVDS, sub-LVDS, SLVS-EC, camera link, and a bunch more. The more common one is sort of the LVDS approach. And so what it does is you drive a circuit, and at the receiver it's got maybe a 100 ohm resistor, and so there's some voltage across that, and so that generates a signal. And what you do is you just change the direction of the current when you want it, as a way of sending a signal, and that way the current flow, the total current flow, is constant. It just changes directions in this segment of the wire, and so that makes the work easier for the current, for the voltage supplies. Also, if you remember, the single-ended wire could have a large ground loop, whereas here the two wires are very close to each other, so their fringing fields start on one and end on the other. And typically they either run on two traces that are sort of matched length, right next to each other on the circuit board, or they run over coax or a twisted pair. So then they can run further, which we'll talk about in a moment. The big exception to this is DVA HDMI. It actually uses current mode logic, so a little bit different resistor configuration than the LVDS approach. What do we do with these? Well, display interfaces. The old one was VGA, which actually sent off an analog, so it had RGB, send and receive, ground, 5 volts, and a couple other signals. Then mostly now, people still use that for retro computers for small applications. DVI is much more common. GVI is completely open source. You can do what you want with it. But it doesn't do audio. So the HDMI is a superset of DVI. It does do audio. And then there are a bunch of other USB-C, DisplayPort, Thunderbolt. These are packet switched displays, and so they're more complex, so require more room in an FPGA. The basic idea in VGA is you kind of do this raster display, you scroll across, you change your colors, and then you return. And also on the new frame you return the electron beam returns. HDMI does something similar, but it also has sort of front and back porches. So there's an image area and there's some time delay between, basically gives the beam some time to come back. And so DVI is very well defined. There's certain dimensions you can use, and they have certain display and front porch and back porch sizes, and there are calculators that tell you exactly how all of this stuff works, online calculators. The other important communication protocol is MIPI CSI. You've got a camera on the left, receiver on the right. You send some pixels, it gets converted to some byte packing formats, goes convert a low-level protocol. There's layer management, there's a physical layer, there can be multiple lanes, various numbers of lanes across, and then all of that gets undone and sent off to the receiver. And don't forget that you have to control your camera. There are typically hundreds or thousands of registers in the camera that need to get set, so the receiver can also send control signals off to the camera. So all quite complex, supporting many different use cases. Kind of one of these things is built by committee. If you want something simpler, what's really interesting is SLVS-EC, sub-low voltage signal EC, originally from Canon, standard from the Japanese Camera Association. The sending protocol, Canon doesn't want competitors, so that's kind of very tightly proprietary. The receiving protocol, a little bit difficult to get access to the specs, but obviously a number of people here have done it. And this will go to higher bandwidths than MIPI CSI. The most interesting thing about this is this will run on a single lane, whereas MIPI CSI requires always at least 2 lanes. And so the European GateMate FPGA has 5 gigahertz lane, and so that actually supports embedded clock. And so there's a good chance that one of these libraries could get ported over there. So all of that's interesting. We should also talk about USB and Ethernet. USB 2 can go up to 5 meters. It gives you 480 megabits per second, of which 300 megabits per second is usable. Not a very large image, but if you do either JPEG or H.256, then it works great as a webcam. USB 3 will take you up to 5 gigabits per second, but only 3 meters. Turns out there's something called USB 4, which takes you up to 40 gigabits per second. I think there's some higher options also. I hadn't even heard about that until recently. There's gigabit Ethernet up to 1 gigabit per second. That'll also should also run on GateMate. The 10 gigabit Ethernet requires multiple. I think it requires 4 lanes at 2.5 gigabits per second, so that won't run on GateMate. Actually, I run the awesome GateMate, so I spend a lot of time looking at that FPGA. If you want longer cables, particularly if you're in trucking or automotive, up to 15 meters, originally there was MIPI C-Phi, but the problem is that was very much controlled by the MIPI, and you had to pay licensing fees, and so the Automobile Association didn't like that, so they created ASA Motion Link. And now we have two standards, so what do? We create a third standard, which is MIPI A-Phi, which is a compromise between the two, maybe more open than the MIPI C-Phi was. The other one that's interesting out of AMD is Gigabyte Multimedia Serial Link, and why I like that is the return path, sort of the controls, the low bandwidth one, can be on a separate wires from the video signal, and so that simplifies the electronics for low volume prototypes. People also want to communicate across wirelessly. If you're doing commercial drones, you don't need frequency hopping, anti-jamming. You can do that with a microcontroller. There's the Runcam Wi-Fi Link version 2, completely open source. The case is open source, the circuit board is open source, the software is open source. You can do with it what you want. This actually brought down prices in this corner of the industry. But you can't do anti-jamming types of stuff. If you're a Python developer, you may like Maya SDR. It runs on AMD's Atom Pluto device, uses the Zinc FPGA and ARM SoC. It's using Amaranth HDL, which is a Python language, which is based on Python language. I think the Blade RF is interesting. So this actually, the core RTL is based on VHDL. And so historically everybody's been moving to Verilog. It's maybe because it's easier, but the problem is Verilog is dynamically bound, and so a lot of VHDL has static binding, so VHDL checks a lot of the errors. And more importantly, if you're able to use some of the AIs do much better with statically bound languages because they know exactly what's legal and what's not. And so I think that we're going to see a rebound of VHDL. I'm certainly moving my work from Verilog to VHDL. We'll see what happens. Okay, so what should you use in your application? Well, it entirely depends. KISS, keep it simple, stupid. If you can find a camera chip or an ASIC which does what you need, use it. By far easiest. If your bandwidth is low, bandwidth requirements low, then you can do libmpix running on Zephyr OS on a microcontroller. Super. If you want to be on the open source, sort of low-end open source, you can run a Raspberry Pi Zero with MIPI CSI to DVP to any FPGA. That'll run you at 1.5 gigabits per second. The Lattice, if you need higher bandwidth, the Lattice NX173340, MIPI CSI and DSI, they support 2.5 gigabits per second MIPI. The 33, you can get the USB. If you need higher bandwidth than that, then you need a closed source FPGA. And of course, for the European-made FPGAs, choose GateMate. Questions? Thank you very much.